Good morning. It's great to be here. I flew in yesterday from Riga in Latvia, coming from the Ubuntu Summit, so I'm feeling very wide awake at this time of the morning, and I'm going to crash horribly about 4 or 5 o'clock this afternoon, but you've only got me for 30 minutes, so that's okay, so I should last. So my name's John Ronco, so I lead segment marketing at SiFive, and I'm going to talk to you about what is RISC-V. I've actually been involved in the RISC-V ecosystem for about a year at SiFive. But before that, I was watching for the sidelines for a very long time because I was at ARM for many, many years, including at one point establishing the competitive strategy team to work out what ARM was going to do about RISC-V. And as the saying goes, if you can't beat them, join them. And so that's why I'm here now. Okay, so what is RISC-V? So fundamentally, RISC-V is an open standard instruction set architecture. Now, the ISA on a chip is super important because this is the interface between hardware and software. And so it's a really critical component of any SoC. All of the legacy ISAs that are out there are proprietary, and they're controlled by a single company. And fundamentally, that's a problem. With the end of Moore's law and the rise in the need to do computing around AI, we're going to need to innovate more and more about how we get performance out of chips, how we get the optimum performance, optimum power, etc. And working with a proprietary ISA is just not going to cut it. So we need a different approach. We need an open standard, and that is what RISC-V is doing. And RISC-V is therefore changing the way that we're going to be building chips for the future. So a bit of background, bit of history. Some of you in this room look far too young to remember much of this. I don't even remember some of this. But this is basically a sort of a history of where instruction sets have been in the computing industry. And you can see that there's some of them have come and go, some of them become popular, some of them become less popular. A number of them have gone through different iterations in terms of who owns them, what the company strategy behind the ISA is. And then some of them have dabbled with being open a little bit, and then sort of undabbled with being open, but none of them have really committed to it. But the key point here really is that you can't depend on an instruction set that is controlled by a single company. I mean, even at the bottom, say something like ARM, which is an instruction set, is relatively open in terms of lots of different companies making chips from it. If you've been dependent on the ARM as an instruction set over the last few years, you've gone on quite a roller coaster with the proposed NVIDIA acquisition, then that being off, and now the IPO, and now being driven by sort of different commercial desires of the company. And so therefore, the key point here is that if you are dependent on an instruction set that is beholden to the whims of one particular corporate entity and its investors, then that can be a challenge. And ultimately, why would you want to bet your future on something proprietary? And it's also worth thinking about what goes into a modern SoC in terms of the number of different cores and number of different processing elements. This example is actually very old, but the situation's got a lot worse since there in terms of being more and more different types of cores that are in there. So even something that might be notionally an ARM-based chip actually has many, many different cores that are not ARM in it. It actually has many different ARM ISAs in it, from like the Cortex-Ms, the Cortex-As, the Cortex-Rs, and the like. But then you have other cores like the GPUs, the TPUs, the DSPs, all these other processing elements, and they all have their own kind of instruction set in terms of how you program them, how you work with them. Now, there's lots of historical reasons why these different ISAs have existed. Some of those are good, some of those are not so good. Some of them were kind of like people just doing things for the sake of doing things, or people doing things because they felt they had to. But the key question is really, do we need them all going forward? And that was really the kind of the founding kind of concept behind RISC-V was do we need all these different ISAs? Should they be proprietary? Why do they keep disappearing? And wouldn't it be better if there was a stable, free, open instruction set that everybody could use for every use case? And that was really the founding principle behind RISC-V. So a bit of history. What happened? So the first question is, why RISC-V? And the simple but disappointingly dull answer is that it was the fifth RISC instruction set that came out of Berkeley University. So Berkeley did a lot of the pioneering work around RISC computing in the early 80s. So Dave Patterson of Patterson and Hennessy fame, or Hennessy and Patterson, depending on which book you read, did a lot of the initial work in the 80s, and they did several iterations of different RISC instruction sets that they worked with. And then for a couple of decades, they generally relied on commercial instruction sets to do the work that they were doing. But around about in 2010, they decided that that wasn't going to cut it anymore, and they needed to do something new. And so they decided, so a group of four of them, so Dave with Andrew, Yunsep and Krista, decided that they would develop a clean sheet ISA as a summer project to help them with some of the research that they were doing. And then once they did that, they then realized the potential that this would have as an open standard that could be used across the whole of the industry, could be used across all of academia, across all of industry, and basically any use case for an instruction set. And so having realized that potential, they decided to launch it on the world. And that led to, in 2014 at Hot Chips, RISC-V being announced to the world, and declaring its goal to basically be a single instruction set that could be used for any computing purpose going forward in any market, in any use case. So a nice modest ambition to start with. But really the point here is because it's open, you can do anything with it. And that was really what the founders were trying to achieve. And it's steadily built momentum ever since. And actually, over the last couple of years, we've seen a real explosion in engagement from across the whole of the semiconductor industry. So anyone who's involved with building chips or building software is really starting to take notice of RISC-V. And there's a huge increase in momentum over the last couple of years. Then just a quick note here on RISCV International. So once they decided to make the RISC-V an open standard instruction set, the team said, right, okay, we need an entity for that. And then RISC-V International was created, and Callista, who was just talking, obviously runs that. And RISC-V International is essentially the neutral, non-profit, member-driven organization that is responsible for managing the standard and basically making sure, basically setting the standard, helping get the members come together to drive the direction it needs to go in, and then ultimately being the custodian of that. Once they publish that, you're then able to do with it what you like because it's an open standard, and that's obviously part of the key benefits. RISC-V International also do a lot of work in terms of growing the communities, working with members, running events like this. So really, they're kind of like the standard bearers for RISC-V in the wider world across all the different use cases. So that's the history, that's the background. That brings us kind of like where we are today. So I guess the question is why? Why is RISC-V gaining this momentum over the last couple of years? Why are all the big semiconductor players and everyone who's in this industry is really starting to take notice of RISC-V? Now at this point I may risk offending some of my engineering colleagues because a lot of them will claim that how RISC-V is better than other ISAs and it does certain things in different ways and that leads to certain improvements in what you can achieve. And actually all those things may well be true. And are true in many cases. But really, the fundamental reasons that RISC-V is getting popular is the business model, is the open standard. It's the freedom to do what you like with it, and the fact that you can use that in every use case, whether that's industry, whether that's academia, whether it's high-end supercomputers, low-end microcontrollers, whatever you're trying to do, there is an applicability to use case. But because of the business model, because of the open standard, you can invest in confidence in what you're doing, you can invest in software with confidence, and that you know that you can have a long-term future with it. So the technical benefits of RISC-V are important, and clearly as a community we should strive to be best in class for every possible use case of RISC-V, and there's a lot of work going on to make sure that is happening. But ultimately the inevitability of RISC-V success, in my view, is due to the nature of the business model, the nature of the open standard in terms of what it offers. So looking a little bit more closely at something around that. So open interfaces in computer science are pretty much accepted. So in a lot of these fields, you can see there were originally some proprietary standards that were being set and that were being managed, and eventually they're being replaced by open standards. And these open standards allow for open source implementations of the standard, but they also allow for commercial implementations based off the open standard. But the general principle of open standards for interfaces has become widely accepted across the industry. And the question is, why should the instruction set be any different? The instruction set is just the interface between the hardware and software on a chip. And the simple answer is, it shouldn't. It really shouldn't be. So that the benefit of having an open standard for the ISA applies just like the benefit of having an open standard in any other interface. And so if we take three of the most popular ISAs and look at, well, what does this mean? What does this open standard mean in terms of the business model? Then with the x86 instruction set, you can get x86 chips from a couple of different vendors, and that's good, but it's not great. It's fairly limited in terms of what you can buy. And if you want to design your own x86 CPUs, you can't do that. If you want to build your own chips using x86 cores, you can't do that. If you want to change anything, you want to add your own instructions, then you definitely can't do that. And you certainly can't have an open source CPU based off the x86 instruction set. So it's not great. Now, ARM is a bit better in the sense that because the way ARM does its business model, it licenses CPUs to chip vendors. There are many, many different chip vendors who are building chips that are compatible with ARM and that you can run ARM software on. So that's a real positive. But if you want to actually design your own CPU, that's possible, but it's very expensive. And it's also quite restrictive, as Qualcomm's found out over the last couple of quarters in their lawsuit with ARM, is that you don't have full control over that. So yes, you can build your own CPUs, but ultimately you're not free to do what you like. And if you want to build a chip to incorporate ARM CPUs, then you can, but you can only buy a CPU from ARM. So if you don't like what ARM is providing to you, then you've got a problem. You haven't got any alternatives. There's not really any possibility to add their own instructions. There is a little bit around the Cortex-M that you can do, and there's certainly no possibility to do an open source core. But RISC-V, on the other hand, you can do all of these things. So RISC-V, there are and there will be many different vendors providing chips that support RISC-V. By definition, because it's an open standard, the architecture license is free, and it's completely free both in terms of cost, but also in terms of freedom, in terms of you can do whatever you like with it. And if you want to buy a commercial core, if you want to build a chip and you want to just license in a CPU for a particular purpose, then there's multiple different vendors, SiFive included, who will happily sell you a high quality production grade CPU. You can add your own instructions, and if you want to do an open source CPU, as many people have done, then you can do that as well. So basically, RISC-V as an open standard gives you the freedom that the existing proprietary legacy ISAs don't give you. So a quick word on SiFive. So as I say, I'm from SiFive. So the three of the guys who founded RISC-V, once they'd handed off the RISC-V instruction set to RISCV International, decided to set up a company, and that was SiFive. And that was a company which the goal was to basically build commercial implementations of RISC-V CPUs. And that's who we are. So today we're the largest vendor of RISC-V CPUs, we've got the broadest portfolio, and everything else. Our business model is essentially the same as ARM's, in the sense of if you want to build a chip, you can come to us and we can license you a CPU. But the critical difference is if you don't like what we're giving you, you can go to someone else and get another RISC-V CPU that's compatible with your software in a way that you can't do with ARM. And that's the fundamental difference, again, about RISC-V. From a SiFive point of view, we announced a couple of weeks ago we've had more than 350 design wins. And so that's with a lot of different major vendors. So Qualcomm, Intel, Google, Samsung, Renesas, Microchip, and a whole ton of other chip vendors globally are using our designs. So that's SiFive. So back to RISC-V, then the growth of RISC-V is really phenomenal, both in terms of what has happened and in terms of what is going to happen over the next few years. So this is data that is actually, I think, a little bit out of date, and I believe RVI are going to be publishing some updated. Yes, Tiffany's nodding at me. There's going to be some updated data on this in the keynotes, I think, later this week, probably tomorrow. But the key thing is not so much the precise number, but just the scale of the growth. So there's already tens of billions of CPUs have already shipped using RISC-V. So actually, if anything, this is quite a conservative estimate, because a lot of people are using RISC-V and they don't have to report it to anyone because it's an open standard. So a lot of people are using RISC-V in embedded cores that you don't even know about, and that's driving up the numbers. And in fact, almost certainly all of you are using RISC-V already, and you may not even know it. So if any of you have a phone that uses a Snapdragon processor from Qualcomm from the last couple of years, that has RISC-V processors in it. The main processor is obviously the ARM processor still, but a lot of the system processors and other processors on the SoC are RISC-V. And basically a wide range of different kind of embedded use cases have already moved to RISC-V. And as I say, tens of billions of CPUs have already shipped in commercial devices. And from my point of view, what's really exciting is we're just entering that phase where more and more of the kind of user programmable CPUs will become RISC-V. So whether that's an apps processor running Android or Linux or a microcontroller, a lot of these things are now moving towards RISC-V. In terms of the rest of the growth, all of the standard educational textbooks have now moved to RISC-V, and RISC-V is now kind of the de facto standard in education. And this matters in terms of having new graduates having a bias towards RISC-V, which is great. And the software ecosystem is growing really fast. Bits of software that didn't have RISC-V support have started to have that over the last couple of years. And software that already had support, that support has been maturing and optimized and is getting a lot better. And this is, this chart, there's a lot on there, so I'm not expecting you to take it all in. It's just a flavor of some of the things that are happening. But it's a mix of open source software and commercial software, and really just illustrates the momentum behind the software ecosystem that we now have. As I'm sure a lot of you know, these things are a marathon and not a sprint. The software gap between RISC-V and other ISAs doesn't get closed overnight, but it's closed really rapidly over the last couple of years and will continue to close. And on that note, I wanted to talk a little bit about RISE. So Jeff Rowe later, I think, is doing a talk to talk about this in more detail. But RISE is an organization that we established earlier this year with the specific goal of accelerating the development of open source software on RISC-V and commercial open source software on RISC-V. And I think what's interesting about this is that this isn't just what you might consider the vested interests, so the SiFives, the Revoses, and the Ventanas, who clearly are very vested interested in getting software working on RISC-V. It's the Googles, the Intels, the Qualcomms, the Samsungs, the MediaTeks, the Nvidias, the big companies who are saying, actually, we see a significant part of our future is going to be RISC-V based, and we now want to really step it up in terms of what we're doing and make sure that the software ecosystem is ready for commercial deployment. And I think that's probably another important point to say about RISE, is that we're very focused on open source software for commercial deployment on Linux capable type devices. RISCV International, by definition, has to be incredibly broad in terms of servicing all the different users of RISC-V, from supercomputers to tiny microcontrollers, from academia to industry, so everyone who's wanting to engage with RISC-V. Whereas RISE is very much saying, okay, how do we deploy RISC-V in high-performance compute, whether in mobile or automotive or infrastructure, that's using Linux and Linux stacks basically on top of it. And so it's a really exciting development. The way we're doing it is through a combination of alignment between the members, but also putting in targeted investment to specific projects that need it. And I think, to be really clear as well, RISE is not developing any new software. We are very much working with the existing open source communities to make sure that they support RISC-V and can support RISC-V fully, rather than trying to create new distributions or new software. So this is a really exciting development. And then, I didn't realize this had a build. One thing I wanted to highlight in particular was Android, as I think this is a really exciting development in RISC-V over the last year. So Lars from Google stood up at the RISC-V Summit a year ago and committed to making RISC-V a first-class citizen on Android. I'm not sure everyone believed him when he said that he was going to do it, but they have done it, and they are very much on track for making what they originally promised, which was Android 15 next year, the release next year, as having full support for RISC-V. And a couple of weeks ago, Qualcomm and Google did a press release where they were talking about their commitment to make wearables using RISC-V, so Wear OS type devices. And that's really great to see that commitment. And I think the key thing here is that where Android AOSP, the Android open source project, is the same across all the different Android form factors. So if we get it optimized for wearable devices and get wearable devices in the field, then there's really nothing to stop it being deployed across all the other use cases of Android. So this is a really exciting development. So one of the things I want to talk about, one of the great things about RISC-V is the freedom to innovate. So the fact that you can have all these different instruction sets, you can create your own instruction sets if you want, and you can do lots of different things. Now, one of the things at this point that detractors of RISC-V will say, aha, that means that you're going to have a big fragmentation problem. So you're going to have everyone doing something completely different. It's going to be chaos. Software's never going to run on it, and it's all a disaster. Now, that's not true, and I can explain why. But before we get onto that, we need to kind of explain the difference between fragmentation and diversity. So fragmentation is doing the same thing in different ways. So the fact that we in the UK drive on the left-hand side of the road, and everyone else doesn't, almost everyone else doesn't. There's a few other people that drive on the same side as us. That doesn't help anyone, do you know what I mean? It makes vehicle manufacturers' lives a bit more confusing, a bit more difficult. It confuses tourists in terms of what they're doing. The world would be a lot better if everyone drove on the same side of the road. So in the same way with instruction sets, it doesn't help anyone if people come up with different ways of doing vector processing. So there should be a single way of encoding vector instructions in RISC-V that everyone uses. And that's really bad. The key thing with fragmentation is to avoid doing the same thing in different ways. But diversity is different. So the Boeing 747 and the bicycle are both transportation devices, and both are really important in different ways. But they both solve very different purposes. And the same is true of instruction sets. So you have 64-bit and 32-bit instruction sets. And even within 64-bit, you have those that are designed more for real-time microprocessors and those that are designed for high-end Linux-capable devices. And it makes perfect sense to have those differences. You don't need everyone to do exactly the same thing, but you need to make sure that you're doing the appropriate instruction set for the different use cases. And so diversity is therefore really important. And you see diversity in the existing instruction sets, whether that's from x86 or from ARM or from anyone else. So diversity is really important, but fragmentation is bad. But with all the different instruction sets, you still have the possibility of fragmentation. So how do we avoid the fragmentation? So really, there's two key things that keep fragmentation at bay. Firstly, nobody wants it. So the users really want to avoid any kind of vendor lock-in or any kind of restriction that says, okay, they can run software only on this flavor of RISC-V CPUs. So SiFive, as a RISC-V CPU vendor, we could come up with some clever way of doing matrix instructions and keep it as proprietary and say it's only ever a SiFive thing. But our users won't want it. Our customers won't want that because they'll say to us, no, we want something that is only standard. And secondly, from a software point of view, nobody can afford to develop their own software stack entirety. So we need to collaborate on that. And the open source software communities are quite rightly only accepting ratified, complete standards from RISC-V and are not trying to support special instructions from different vendors. So if everyone focuses on just supporting the ratified standards, then a lot of fragmentation can be avoided. Now, you still have a bit of a problem in terms of just the number of different extensions that are possible with RISC-V, and the fact that you can have all of those and you could combine those in many different ways. You actually need to a very large combination space in terms of the number of different options that you have. And that's great for some use cases. So if you're doing a deeply embedded processor or you're doing a very specialist processor, you probably want to have that flexibility to choose exactly what you want. And I think the next speaker will talk a little bit about that, because that's clearly part of what CodaSIP does. But if you're wanting to do a Linux distribution, you really, really want all of the different RISC-V CPUs from the different vendors and the chips from the different vendors to be the same. You don't want to be having them as all completely random and different. And so that's where the profiles come in. So what we are doing with the profiles is basically packaging specific sets of ISA instructions together, ISA extensions together, and saying, right, okay, that is a set of mandatory instructions that everyone is expected to support for a particular use case, and then a limited set of optional instructions that can be added on top. And so for Linux distributions, it's the RVA profile. And so RVA 20 was published a couple of years ago, RVA 22 last year, and we're just in the process of trying to ratify RVA 23 as the next generation. And I mentioned Android on the previous slide. Android, Google have said very clearly that for Android devices, they expect RVA 22 plus vectors plus vector crypto. So it's a very specific set of looking at the profiles and saying that is what you need if you're going to support an Android device. And we're not going to support Android on lots of older devices that don't support this. So this is a kind of way of kind of keeping the ecosystem together and focused. So that's the profiles. But then actually the ISA by itself isn't enough. If you're, as I say, if you're building a Linux distribution, you would like certain non-differentiating things like how interrupts work, how the boot flow works, to just be the same. You want things like that to just be there and consistent. And that's what we're working on with platform standards. So if you're familiar with what ARM has done around System Ready and SBSA, this is essentially the same thing, but looking at it from a RISC-V point of view. The ultimate goal here is just to make software really boring and work and just run out of the box, so you don't have to do lots of work to port software between different platforms. So that's ultimately the goal of the platform standards. And then I won't dwell on this just in terms of instructions, but just give you a flavor of some of the instructions that have been ratified in 2023. The main thing really, I think, to just take away from this is that, one, there's a lot of things happening, so there's a lot of instructions are being ratified, but also the completeness of the ISA is now pretty good. It's actually pretty comparable to the legacy ISAs that are out there in terms of some of the instructions and some of the capabilities that there are. There's more to be done for sure, but there's an awful lot of, you can now build really, really capable RISC-V CPUs for any market with what's been ratified. Okay, so to conclude really, so RISC-V has huge momentum and is, in my mind, is very much now unstoppable. It will have the best processors, it will have the best ecosystem. I think that is now inevitable. And the inevitability is not just because of the technical superiority, although there is some of that, but it's fundamentally down to the business model. And it's a business model that is wanted by all of the major players across the semiconductor industry. And that is fundamentally what is driving the growth of RISC-V and what is going to make the next few years incredibly exciting. So thank you very much. Do we straight to the next person, or any questions, or any questions? Yeah, questions. Yeah, I mean, I think it's, yeah, I think that's true. I mean, I think there's a lot of work that needs to happen in terms of software, hardware, co-design to get the best out of it. But I think that your key point, and this is the reason why a lot of companies have embraced open standards and open source, is that there's a lot of stuff that just needs to be there. And they don't want to invest in that themselves. They want to focus higher up the stack. And I think you're right. I think that is part of what's driving the momentum behind RISC-V. In terms of the decision making within RISC, yeah, I mean, I think inevitably there are some louder voices within the standard setting bodies in terms of how RISC-V is driven forward, but it's more democratic in terms of it's across a range of different companies that are working together. And I think that's okay, actually. I think you want, do you know what I mean? The biggest companies with the biggest vested interests, you want to be driving a lot of this. But also, because the freedom is there to innovate, if people want to do something slightly different and prove out a different way of doing things, then there's the opportunity to do that. and then steer the community in that direction. And you can see that happening with the way things that have happened over the last couple of years. Different people are coming with different ideas, and it's moved beyond just being a couple of people saying, right, this is the instruction set, to other companies proposing things, and that's what's really exciting. Okay, well, maybe one more question if anyone's got it, or no? Oh yeah. I think it's both. So the question was, is it general purpose computing or purpose built? And I think it's both. So I think if you're doing something very specific, so you're designing it for a specific purpose, the fact that you have massive amounts of freedom to innovate around the CPU, around instructions and what you do, makes RISC-V absolutely ideal for that. But for general purpose, the fact that different people can build different CPUs that are suitable for, that can support the same instruction set and support the same platform standards, mean that you're ultimately going to get better chips, and you're ultimately going to get better systems to support general purpose software as well. So I think what you've seen so far with RISC-V is RISC-V has gained a lot of momentum around maybe more deeply embedded and maybe more maybe more single purpose use cases. But I think that's just the foundation. As I say, we're now at the point where we're starting to see more designs moving into the general purpose space, and that's what's going to be really exciting over the next couple of years. Cool, thank you. Oh sorry.